This is the screencast for section 8.2, example 3, using L'Hopital's rule with one-sided limits. So we're going to evaluate the following limits using L'Hopital's rule. Support our answer graphically. Part A, the limit as x approaches 0 from the right of the sine of x over x squared. So first of all, you can see the sine of x over x squared is going to have a different limit from the right than it does from the left. So we're going to explore that limit from the right. Now if I plugged in 0, I would get 0 over 0. So L'Hopital's rule might be a good idea for this. I know we have another way you might be thinking, the sine of x over x, we know the limit as x approaches 0 of that, and then you'd multiply by 1 over x. We've actually done this problem before, way back in chapter 2, but now we have a different way of going about it. So let's try it. We will take the limit as x approaches 0 from the right of now the derivative of the numerator over the derivative of the denominator. So can we plug in 0 this time? Well, yes, we get 1 over 0, but remember, x doesn't actually equal 0, it's approaching 0 from the right. So as our x values get really tiny, 1 divided by those really tiny numbers is going to produce positive infinity as its limit. So 1 divided by 0.9, 0.7, 0.6, 0.1, 0.0001, 0.000001, all those values get really high up to infinity. Part B, the limit as x approaches 0 from the left then of the sine of x over x squared. Well, if I plug in 0, I get 0 over 0. So L'Hopital's rule is a good candidate. I will take the limit as x approaches 0 from the left of now the derivative of the numerator over the derivative of the denominator. Yes, we already knew that. But now it's a little bit different because I'm going to get 1 over, this time, a negative 0. And yeah, I know there's no such thing as negative 0. But what this means is if we're approaching 0 from the left, we're not talking about 0.1, 0.01. We're talking about negative 0.1, negative 0.01. So 1 divided by these negative numbers that are getting really close to 0 is not going to produce positive infinity. It's going to produce negative infinity as its limit. So that's what's going on here. This function, the cosine of x, is getting divided by values getting very close to 0, but negative values. So positive 1 divided by negative values would produce, or negative teeny values would produce negative infinity. Then now try problem number 11. Says you use L'Hopital's rule to evaluate the one-sided limits and support your answer graphically. Alright, so first I'm going to plug in 0 and see what I get. Surprise, surprise, I get the indeterminate form 0 over 0. So now I'm going to take the limit as x approaches 0 from the left and use L'Hopital's rule. So now I'm going to use the derivative of the numerator over the derivative of the denominator. And I get 1 over 0, but again, this isn't 0, this is 0 approaching from the left, meaning all these numbers are negative getting plugged in for x, but they're being squared, so they're still positives. So this will produce a positive infinity as my x values get closer and closer to 0 from the left. So the limit as x approaches 0 from the left is going to be positive infinity. Now let's look at part B. Again, I plug in 0 and I get 0 over 0. So L'Hopital's rule, the derivative of the numerator and denominator I already established in the first part. So now I need to think about what's going to happen as I plug in 0 from the right. Well, it's the same thing as before, because now when I'm plugging in, as I approach 0 from the right, I'm plugging in teeny tiny positive numbers, which are squared, still positive. It's the same situation, 1 over 0. And we're going to get close to, we're going to approach positive infinity. Now let's check that graphically. And by graphing the original function in y1, you can see that the limit as x approaches 0 from the left is positive infinity, and the limit as x approaches 0 from the right is also positive infinity.